Welcome and thank you for joining. In this lesson, we'll explore the derivatives of primary trigonometric functions. So we'll learn how to differentiate the functions y equals sine of x, y equals cosine of x, and y equals tan x. So we're going to go over the proof together. And before we do so, let's recall two very important limits in trigonometry. The first one is what we call the limit of sine. So the limit as x approaches 0 of the function sine x divided by x equals 1. In order to best understand how the limit as x approaches 0 of this function is equal to 1, it's enough that we take a look at the graph of it. So here is the graph of the sine x over x, so the blue graph. As you can see, when the x values approach 0 on the right-hand side, the y values become 0.999. And when x values approach 0 from the left-hand side, the values of y will approach 0.999. And exactly at x equals 0, the function is undefined. And that is understandable because the denominator is just x. And when x becomes 0, the denominator becomes 0, which makes the entire function undefined. So in other words, then, we're going to say that the limit as x approaches 0 of sine x over x equals 1. The second important limit that we will have to use in order to prove the derivatives of trig is the limit of cosine. So we say that the limit as x approaches 0 of cos x minus 1 divided by x is equal to 0. And again, we're going to do the same thing here. We'll revisit decimals. We're going to take a look at the function cosine x minus 1 divided by x, which is this green graph here. When x equals 0, as you can see here, the function is undefined and the graph of it will present a hole as a result. And as you can see again, when the x values get very close to 0 from both left and right hand side of it, the values of y will approach the same number or the same value 0, which means that the function is undefined at x equals 0, but the limit exists. So the estimated values of y around 0 are approaching the same number, so number 0, and that makes the limit of cos x minus 1 over x equals 0. So let's start off with proving the derivative of y equals sine x. So the derivative of y equals sine x is equal to cosine of x. And obviously, if we have a function inside the angle, inside the sine, that means that we have to apply the chain rule and multiply by dy dx, du dx, which is the derivative of the inside function. So as we have always done in the past, when proving the derivative of a function, we always use the first principles formula. And that's the reason why we call it the first principles formula. So we're going to start off by finding dy dx, or the derivative ddx of sine x, which for short, I will write it as sine of x prime. So if we use the derivative, it means that if we use the first principles formula to find the derivative, it means that we will have to find the limit as h approaches 0. And let's get started with the first term, f of x plus h. So if f of x is sine of x, it means that f of x plus h will be found by replacing x by x plus h. So that will make sine of x plus h. And then minus f of x is sine of x, and then divided by h. So as you can see here, this is an indeterminate form limit because as h approaches 0, the denominator becomes 0, which means that this entire function here that represents the derivative of sine of x is undefined when h becomes 0. So we will have to find the approximate value of it. So, or in other words, just the limit. Now recall again, how did we find indeterminate form limits? To determine or to find indeterminate form limits, we had to simplify the expression inside the limit up to a point where h became insignificant. Okay, so we simplified it, in other words. So the main goal when we are proving the derivative of sine will be to somehow eliminate the h from the denominator. And we have to do this step by step, slowly and with patience. We have to look into each and every term. And even when we don't have a clear idea of what the algorithm would be, when proving something, we always think, like in every step of the solution, we must think, what are simplifications that I can apply to this formula? What are terms that I can replace, and what can I replace them with? Or how can I change the expression so that it looks different, so that I can somehow figure out a way to simplify what I need to? So as you can see here, we have the difference of two terms, and the sign of x is pretty simple, like it cannot be broken down into anything else. But as you notice here, we have the sign of x plus h, and you probably recognize the sign of the compound angle formulas. Remember that sign of x plus h is, or it will follow the formula, the sign of a plus b equals sine a cos b plus cos a sine b. Cos A sine B. So we're going to apply this same formula that we have learned in the advanced functions course for this limit, and we're going to say that would be the limit as h approaches 0. And here we go again. We have the sine of x cosine of h plus cosine of x sine of h, and then minus sine x, that would be this term right here. Okay, so let's highlight them so that we have an idea what's going on here and where the terms are going. Okay, and then divided by h. So once we have brought the entire function in this form, then we are thinking, how are we going to simplify h? For this, we are going to try to bring in the derivative sine of x over x, which you can also imagine or express it as sine of h over h, right? So it's the same idea, the same formula. You can use any variable of your choice. So if we be able to somehow factor a sine h over h, whose limit we already know, then this way we can eliminate the h that is making the limit indeterminate. So let's take a look and see what we can do. So I noticed that the sign of h appears in this part of the formula and of the equation. So what I am going to do, or what we're going to do next, is we have to think of grouping the terms so that sine of h can be simplified somehow. So remember that here we have three groups of terms, so they are separated by a plus and a minus. And what we want to do is group terms that have something in common, so a term in common. And as you can see here, we have sine x cos h and sine x that have sine of x in common. So we'll bring them together. So again, we are following the strategy, simplify as much as possible, transform as much as possible, and check and see if there are patterns that can help us get to the solution. So, and then we have plus cosine of x, sine of h. Now, notice that now we have, sorry here, my bad. So notice that here we now have a common factor of sine of x. We have h in the denominator. And when we have sum and difference of terms, actually, we can split the fraction into two. And this is the next thing that we want to do, is we are going to give an h to each. We're going to give an h to each fraction here. So we're going to keep this in brackets, the entire thing in brackets, and that would be equal to the limit as h approaches 0. And here we are taking out the sine of x. In brackets, we'll have cosine of h minus 1 divided by h. So we're taking out sine of x, right? And cos h minus 1 over h is inside the brackets. And because this is multiplication, only this part will keep will have the denominator. Now, remember that one of the limit properties is that the limit of the sum equals the sum of the limits. So what that means is that we are going to rewrite the rest of the expression as the limit as h approaches 0 of cosine x sine h divided by h. So as you can see in here, the expressions or the limit is kind of shaping up. I notice that I have sine h over h in here, and I have cosine of x, which is not even dependent on h. On the other hand, here we have sine of x. This is a term independent of h, and we have this important limit in here, which is equal to 0. So to make everything formal and write everything in proper form, what I will do is separate the limits again. We know that the limit of the product would be equal to the product of their limits. So what we have here is the limit as h approaches 0 of sine of x multiplied by the limit as h approaches 0 of cosine of h minus 1 divided by h. And then we have plus, so this plus in here. And we are applying the same idea in here. You have cosine of x times sine h over h. So we will rewrite or split this limit into the limit as h approaches 0 of cosine of x multiplied by the limit as h approaches 0 of sine h divided by h. Let's see what we have created here. So if you look at this limit, the limit as h approaches 0 of sine x would equal sine x. That's because h cannot go anywhere in here, so sine of x is independent of h. So you can look at it as the limit of a constant, so it would equal sine x. Now we're multiplying this, so you probably recognize in here the limit of cosine. So cos x minus 1 over x is 0. So therefore cos h minus 1 over h equals 0. So multiplied by 0. And then we have plus the limit as h approaches 0 of cos x equals cosine x for the same reason as sine of x that we explained in here, this term in here. And then multiplied by, we know that the limit as h approaches 0 of sine h over h is equal to 1. So what we obtain in this case is this product here, which is equal to 0, plus this product here, which equals cosine of x. So remember that. That would be the value of the limit as h approaches 0 of sine x plus h minus sine x over h, which represents the derivative of sine x. So we'll say that cosine x is the derivative of sine x. So, and with this, we have proved the derivative